So this is E658 lecture 45, is it? So yesterday we were talking about how to realize a first order delta sigma modulator using a continuous time loop filter. I showed you yesterday that it is indeed possible. We'll today spend some more time looking at this and figuring out why it's any better than doing it in discrete time. One problem that we recognized with respect to the discrete time modulator was that since you're sampling before you get into the ADC, you need an anti-alias filter. Okay, perhaps since you're sampling in this continuous time delta sigma modulator, you're sampling at the output of the loop filter, so perhaps the aliasing function becomes easier. It could be tougher also, but let's take a look. And before I get there, I want to clarify a couple of points. The sampling rate is 1 Hertz. This is V. This is Y of T. This is Y of N or Y of K. This is V of. Alright. So one thing I wish to point out, because there seemed to be some confusion at the end of the class yesterday, is the nature of this quantizer. See, a quantizer is basically a nonlinear block with the following input-output transfer curve. Alright. So the dimensions of if the dimensions of the input are in, say, volts, the dimensions of the output are also in volts. Okay. Alright. So the question is, how will you realize this quantizer in practice? An ADC followed by a DAC alright. So this was Y and this was V. So here, which is Y and which is V? The output of the DAC is V. Alright, the input of the ADC is Y. Okay. What are the dimensions of this chap? Volts. This chap? Volts. Okay. What about this guy here? This is completely dimensionless, right? It's a binary number, right? So if you have a 4-bit converter, there will be 4 wires running between. In principle, there will be 4 wires running between the ADC and the DAC. Does this make sense? Okay. So where is the quantization noise being actually added? At the input of the ADC, right? So Y, alright, and this is how you get the P. Alright. So when you embed this quantizer in the question I was asked after the class yesterday was, if the quantizer is embedded in a feedback loop, then all we need to do is replace this chap with this contraption here. Alright. Okay. So in which case So this is Y, this is V of n, V of t actually, right? Because this is continuous time, the DAC converts a discrete time output into a continuous time output. All right. So which is the output of your delta sigma modulator? The output of the ADC. Why? Why can't I take the output V of t? Pardon? So, see, please note that this is an analog to digital converter. I want analog input, voltage in and bits out. Okay? Alright? So, this is the delta sigma ADC output. Alright? So, if I had just a 1-bit quantizer, that is 2 levels, what will the output be? The output here, what codes will it consist of? It will consist of either 0 or 1. So, if I look at the output in the time domain, it will be let me see. All right. So this is the code in the of the delta sigma output in the time domain. All right. So given that this is only running between, it's only 1 bit, how am I going to get 16 bits or whatever at the output of the, you know that I'm going to pass this through a digital filter. And then downsample, and I'm going to get equivalently 16-bit. Let's say I designed the noise shaping properly so that I get my delta sigma modulator in-band SNR is better than 95 dB or 96 dB, so that I'm expecting a 16-bit word. The input is only 2 levels. How am I going to get 16 levels? 2 to the 16 levels. Yes. Yeah, so please note that, in the simplest case, you can, one simple way of realizing a digital filter is use an FIR filter, which is basically sigma k C of k or W of k, the kth tap, times V of n minus k equal to 0 to n. That's the filter output here. Alright. So these WKs, which correspond to the weights of the filter, okay, will all be, if you are to get 16 bits out here, this must be at least 16 bits long, right? And when you add all these things up, you will find that there will be round off error and so on, but you will finally truncate the output to, when you add two 16-bit numbers, the number becomes 17 bits, right? So you do all the addition and then truncate off all the extra stuff. Okay, you take only the 16 most significant bits. Does this make sense? Alright. So there is a distinction to, this is what do you understand when you say it's a digital filter? How do you think it's implemented in hardware? So that is a problem. So see, a digital filter is to be distinguished from a discrete time filter. Okay, a discrete time filter is a filter where the signals are continuous in amplitude but discrete in time. Okay, so all those, so this is exactly, when you open Oppenheim and Schaefer and mug up all those equations, all those things refer to discrete time signals. That's why it's called discrete time signal processing. The book is not called digital signal processing. You understand? The assumption is that once you master those techniques, the jump from discrete time to digital is very straightforward, in the sense that what is the difference between a discrete time filter and a digital filter? In a digital filter, the amplitude levels are also quantized. Okay? Does make sense? So once the amplitude levels are quantized, you do not need to keep track of a bazillion continuous levels. You need only finite number of levels, which means that you can represent each of these levels by a unique code word, right? And then filtering just simply becomes manipulating of these code words. Does make sense? Okay? So register length, all the hardware involved in a digital filter is basically gates. Okay? Gates, flip-flops, which are basically delay, and you can use gates to make a multiplier, adder, and all this wonderful stuff. Does this make sense? So how do you think you'll implement a discrete time filter? So one way of implementing discrete time filters is to use switch capacitor techniques, where everything is sampled but the amplitude levels are all continuous. Okay? There is a big distinction between the two. Does that make sense? Alright. The reason I am going through this is that after yesterday's class, a couple of people asked me this, and then I found, kind of struck me that a lot of other people would also have this, possibly have this confusion. Okay? So, yes?
Can you please explain again how we are getting 16-bit out of this?
So, okay. Alright. So, the output of the ADC in a single bit case is basically either 0 or 1. Alright. So, and if you, you take this and filter it through a low pass filter. One example structure of realizing a low pass filter is simply an FIR structure, which is simply nothing but a weighted sum of delayed samples. So Wk times V of n minus k. So if Wk has got 16-bit precision, correct? Then by adding a whole bunch of 16-bit numbers, you will get, and you truncate off, all this extra stuff. You take only the MSB, the significant parts of that 16-bit sum, right? Then you will get a 16-bit word. You understand? So even though the levels at the input are 0 and 1, this 0 and 1, this 1 stands for the MSB of the 16-bit converter, of the 16-bit register. You can think of this as, what do you call, 0, 0, 0, blah, blah, blah is one level, and 1, 1, 1, 1, 1 as the other level. Okay, so it's either all zeros or all ones. Okay, and by averaging, you are generating a whole bunch of numbers which lie between the all zero code and the all, the all zero number and the all one number. If you have a register length of n, the largest number you can represent is 1, 1, 1, 1, 1, 1, which is 2 to the power n minus 1. Similarly, the smallest number you can represent is 0, correct? So to get all numbers in between, you basically you're averaging the largest number and the smallest number in some weighted fashion, correct? You're doing some clever averaging of the large number and the small number to get, in principle, any arbitrary number between the two of them. You understand? Is that clear?
How is it equivalent to 16-bit quantizer? How is this thing equivalent to that?
No, I
am making it 1-bit quantizer look like a 16-bit.
Yes. So once you average out the these numbers, okay, then you will get so this is very simple. I showed you this stuff earlier on, where I took just a simply a coarsely quantized input, and you pass it through a smoothing filter. A very low pass filter, which cuts off all the high frequency components of the noise. Then what happens if you take a step like quantized waveform and pass it through a low pass filter? What happens? All the steps get smoothened out, which is equivalent to saying all the high frequency components of the input get filtered off, correct? which means that if you look at only the energy within the signal band, there is signal and is this. So this is the signal, okay, the sine wave, and if I just quantized it, this would be the quantization noise, correct? Now if I take a filter, a sharp filter, and cut off everything beyond the signal bandwidth, what happens? The output spectrum is basically looks like this. So I realize that this is now a vastly oversampled signal, right? Because the highest frequency component in this signal is basically just the corresponding to the big wall filter, correct? So I can actually downsample this by the oversampling ratio, and I'll end up with a signal finally with a signal to noise ratio corresponding to this guy divided by only the amount of noise in the signal band. So, and this noise is all coming why? Deepa Devendran. It's all quantization noise. You understand? So you're taking a poor quantizer which added noise all over the place, okay, cutting off all the stuff outside your signal band, and the in-band signal to quantization noise ratio looks like a more precise converter. Is that clear? No? Almost. Huh? Okay, let me ask you a question then. So, if I didn't do any low pass filtering and I downsampled it, what do you think will happen? Pardon?
Noise will all alias back.
Yeah, and what will happen?
Won't reduce anything.
It will increase by Oversampling.
Okay, the question is the following. I take a sine wave, okay, so 1 kilohertz sine wave, let's say for argument's sake. I sample it at, let me take an OSR of 64, so I sample it at 128 kilohertz. I pass this through a quantizer, say a 5-bit quantizer. Alright, and the amplitude is 1 volt for the sine wave, and the quantizer range is 2 volts. So that basically means that the sine wave is exactly fitting in the quantizer range. The quantizer is not getting overloaded, right? So if I look at the output, the spectrum will be what? It will be the 1 kilohertz sine wave here, alright, up to 64 kilohertz. This is Fs by 2, and quantization noise will be like this. Okay, so what is the mean square value of this quantization noise in relation to the signal power? If I take the signal power and find, and then divide the signal power by the total noise power, which is basically the mean square value of the quantization noise, what will I get? Huh? I should get 31.76 dB, 6n plus 1.76. You understand? Alright. Now if I took this signal and then downsampled it by a factor of 64, alright. So that this frequency is 2 kilohertz, which is basically the Nyquist sampling rate corresponding to the input. Now this will also have quantization noise, correct? So what do you think if I took the power of the signal here? So SNR at this point is 31.76 dB, which corresponds to 6 times 5 plus 1.76. Alright. Now if I downsample by 64, what do you think happens? Huh? Yes. Okay, I mean those who claim to have understood the previous discussion, can you tell me what happens to, what will happen if I downsample the whole thing by 64? The noise will? Why do you think the noise will keep on adding up? So as you guys point out, the noise spectral density will go on, if you look at it in the frequency domain, so noise spectral density will go on aliasing, right? So this stuff will come on here, this stuff will also come on here because I am sampling it at, resampling this thing at downsampling it, just dropping samples. You understand? Alright, so clearly the spectral density is going on adding up. What happens to the bandwidth? Is reducing, so what happens to the total thing? Should remain the same. Does it make sense? Another way of thinking about it is that if I thought of this quantizer as an additive noise source, this is a this is a white noise source with a mean square, some mean square value, correct? So if there is a, when I say it's a white noise source, what does it mean? It means that in the time domain, it means that neighboring samples are completely uncorrelated. If I find the mean square value of sample 1, 3, 5, 7, 11, etc., it must exactly be the same as the mean square value of 2, 4, 6, 8, etc., which means that whether I drop samples or don't drop samples, the mean square value must remain the same. Okay, which is equivalent to saying, which is the time domain view of the same phenomenon. You understand? On the other hand, if I put a low pass filter here and then drop samples, let's say I put a 1 kilohertz low pass filter here. Alright, so it just lets the input tone through and then cuts off everything else. What do you think I will get? The SNR will increase, the signal power will remain the same, the noise power will reduce by a factor of 64, correct? So my signal to noise ratio will increase, by that factor of 64 or 10 log 64 dB. Does this make sense? Okay. So if this whole thing was put in a black box now, alright, then this looks like an Nyquist rate converter, not this. If I put this whole thing in a black box, this will look like a Nyquist rate converter with in-band, it's a Nyquist rate converter, so if 1 kilohertz was there, that basically means that you're sampling at 2 kilohertz, alright, or the input bandwidth of the Nyquist converter is 1 kilohertz, and the signal to quantization noise ratio looks like, no, it's not 10 bits, it's basically, it increases by a factor of 64, right, so the in-band SNR will be 31.76 dB plus half a bit for every doubling of the OSR. So you are getting 2 to the power 6 times, that is 6 times half is 3, right. So plus 3 bits, which is basically, it looks like an 8-bit converter. Although you have used only a 5-bit ADC. Is this clear? Okay. All right. Okay. So the oversampling A to D converter is doing better by simply, yes. Yes. Oh, okay, so if you made, the question is if you made WK a 32-bit precision number rather than a 16-bit precision number, are we going to get 32 bits out equivalently. The answer to the question is yes, provided the in-band quantization noise is smaller than that number, correct? So see, please note that the spectrum coming out of the sigma delta ADC is something like this, alright. So, and what I am doing in principle is cutting off stuff like this, correct? And if you want to realize a magnitude response like this using an FIR filter, you can go and use all the techniques that you learned in DSP to go and find the coefficients of the FIR which will give you this kind of magnitude response, okay. At this point in time, the coefficients are still infinite precision coefficients, okay. So even with infinite precision coefficients, you can only get the in-band SNR which is corresponding to the noise that filter lets through, okay. The next step, once you find the infinite precision coefficients, is to truncate the coefficients, because you know that in a practical DSP, register lengths are always finite, okay. It turns out that when you truncate these coefficients to finite precision, then the frequency response can get altered, because the coefficients that you have now for your filter are not the same as what you intended to have, okay. And in some filter structures like IIR filters, it turns out that, I mean, this is equivalent to overloading if the coefficients or register lengths are finite, it is like chopping off internal node variables so that they cannot go beyond a certain range, okay. So such effects or such errors are called round off errors, alright, okay, and saturation errors. And it turns out that in some digital filter structures like IIR filters, because of practical difficulties associated with finite register length, some structures can actually go into oscillation, okay, because of coefficient truncation, alright, which is one reason why a lot of people prefer to use FIR filters, because there is no feedback, it's always feed forward, right. So there is no recursion at all, alright. But thankfully in today's DSPs, register lengths are not an issue at all. This used to be a problem 10-15 years ago, and everybody and his brother were working on what happens if you go and take this filter structure and cut off its coefficient, the register number of bits by 2, and then you find that you get 0.2 dB more SNR, and then you have some optimized structure and you write some paper and so on, right. But now hardware is so cheap that you throw 3 more bits, nobody bothers. So unless you're doing some super optimized, where you want to count every gate, which doesn't happen very often, people don't really, which is why the original book, Oppenheim and Schaefer, was called Digital Signal Processing. This was, during my days, when discrete time signal processing had, I think, barely just come out. The first book was called Digital Signal Processing. Then they changed the name of the book to Discrete Time Signal Processing, okay, because the two are fundamentally not, they're not the same, definitely. You understand? So, the short answer to the question is that beyond a certain precision, okay, you can't do any better than the inherent quantization noise within the signal band. Okay, if you quantize the coefficients, you're probably doing as well as or slightly worse than what you would do with infinite precision coefficients. Is that clear? Alright. So, an oversampling converter is basically what it is doing is, not only is it oversampling, it's also shaping noise outside the signal band, so that the in-band quantization noise, signal to quantization noise ratio is now greatly increased. Alright. And as I said yesterday, it is possible to realize the loop filter using continuous time circuitry, and we saw yesterday how this was indeed equivalent to so this is the pulse shape of the DAC. We considered the NRZ and the RZ pulses. for this particular case of a first order modulator, we found that whether you use an NRZ pulse or a return to zero pulse, the noise transfer function remains the same. Alright, and the sampling rate is assumed to be 1 hertz. Okay. Now, if I want to make a sampling delta sigma converter with a sampling rate equal to 100 hertz, what would I do? This represents a first order delta sigma modulator with an NTF of 1 minus Z inverse, and the sampling rate happens to be 1 hertz. Okay. Now, if I want to realize a delta sigma converter, a first order one where the sampling rate is not 1 hertz but 100 hertz, what should I do to the to this modulator? What should I do to these things? I mean, should I go and recalculate everything, or should I? Pulse shape of PT will change to what? Right now, what is the pulse shape? It's 0 to 1. Okay. All right. So if I now run the modulator at a rate of 100 hertz, what will happen to the pulse shape? It will become 1, and the time axis will become 0.01. Correct. So okay. And what else? So, pardon? No. The pulse shape will still remain 1. What should I do to make sure that the do you guys, the O5, do you guys understand the question? No? Okay. So, we have, okay, I have given you the diagram of a modulator with a noise transfer function of 1 minus Z inverse when the sampling rate is 1 hertz. Okay. And why do you think changing the sampling rate will, before I go there, what do you think will happen if I change the sampling rate? Everything is the same. I just change the sampling rate. What do you think will happen?
Might take samples. Earlier we had 0 first this thing and 1 else.
Can you come again?
The discrete time output was discrete time output was 0 at n is 0 and 1 everywhere.
Discrete time output of what?
Vn.
Vn. No. Oh, first of all, before getting into all the math of the thing, what do you think will happen? Do you think something will change? Nothing will change. Loop gain will change. Why? Why will the loop gain change?
Taking the samples at the wrong time.
Yeah. So I'm taking the samples at the wrong time. Earlier, everything was working nicely because so at 1 hertz sampling rate, the pulse shape was this is P of t, this went into an integrator giving rise to a continuous time output like this. So this is 0, 1, 2, etc. Alright, and I am sampling at 1 hertz. So these are the samples, correct. Now if I change the sampling rate to say 100 hertz, what happens to the pulse shape? What happens, Joish? What is the height of the pulse? It will remain 1. What happens to this guy? This goes to 0.0 to 0.1. 0 1. Why?
Sampling rate is
Yeah, that's what I said. Yes, but why do you think the
so it should run from 0 to 1 over.
I mean the output of the DAC will update at, instead of updating at 1 second, will update every 0.01 seconds. Correct? So this is the pulse shape. Now if I didn't change the integrator at all, the integrator is still 1 over S. What do you think will happen to the output? It will go to 0.01. Alright, which is the area of this pulse. At what time will it stop ramping? Ramping up 0.01 seconds, and but I'm sampling at 0.01 seconds. So what I will get is, instead of getting 0, 1, 1, 1 as the loop gain impulse response, I will get 0, 0.01, 0.01, 0.01, etc. Correct? So the changing the DAC, changing the sampling rate of the A to D converter has got two effects. One, the pulse shape width is reduced, okay, and two, if I left the loop filter as it is, then clearly the loop gain has changed. The samples of the loop gain are completely different now. Okay. So what should I do to fix the problem? What should I get? I should get 0, 1, 1, 1. So what should I do? I should multiply this by 100. Okay. So in other words, if I multiplied this by 100 by S, this should go to 0, 1, 1, 1. Alright? You understand? It's very simple. All that I have done is scale time. Correct? So if an electrical network, if I changed everything in the network with dimensions of time, what do you think will happen to the impulse response?
Go down by a factor of 6.
Okay, let me give you. In an electrical network, if I change all the poles, if S by omega p, if I had let's say I had a transfer function of the form S by omega p square plus 1 by qp S by omega p plus 1, and this say corresponds to an impulse response of h1 of t. Alright. Now if I made this 4 omega p, what will happen to the impulse response? It will be t by 4. Alright. In other words, what has happened here? I have increased all omega p's by the same factor. In other words, every quantity with dimensions of time, 1 over omega p has got dimensions of time, correct? I have scaled all quantities which have dimensions of time by a factor of, reduce them by a factor of 4, alright, which means that the impulse response will have the same shape except that it will be scaled in time. Does this make sense? Okay. Yes, sir.
So suppose we have the ability to generate a pulse shape of 100 volts.
Yes. Yes.
Then doing that and keeping the loop gain same as before.
Yes.
Wouldn't it?
Yeah, that will also work. Correct. So in this particular example, what he is pointing out is the following, which is, instead of putting the gain of 100 in the integrator, you could have put the gain of 100 in the pulse shape. Okay. In this particular case, it definitely works, but you will see soon that in general it doesn't work at all. Okay. This is the first order example, is one case where it doesn't matter whether you increase the pulse shape or the amplitude of the pulse shape or the gain of the integrator itself. Does it make sense? So here, so what have we done here when we scale this we scale the sampling rate from 1 Hertz to 100 Hertz. All that you need to do to make it work properly again is what are all the things in the network with dimensions of time. One, of course, is the clock rate itself, which we have increased by a factor of we increase the clock rate by a factor of 100, which means that you reduce the time period by a factor of 100. Okay. What else is there here with dimensions of time? This 1 over s, correct? The 1 over s is nothing but the input output is dimensionless. So the numerator must have dimensions of, what are the dimensions of s? Frequency, which is Hertz, right? So the numerator must also have dimensions of what? Of Hertz, correct? The numerator has got dimensions of Hertz, the denominator has Hertz, the Hertz goes away and you get no dimensions, right? So the only other thing in this chap, which is in this network, which has got dimensions of time, is basically the gain of the integrator, right, or the time constant of the integrator. And if you have to, since you have reduced the pulse width, if you reduce the width corresponding to if you reduce the time constant corresponding to the integrator, you will also you should get back to all things with dimensions of time have scaled by the same amount, correct? Which basically means that the shape of the impulse response will remain the same. In other words, the samples of the impulse response in this particular case will remain the same. Alright. So what should I do? I have reduced this by a factor of 100. So I must increase the numerator by a factor of 100. Correct? So this now can be applied blindly to any modulator without even going and calculating the noise transfer function. Correct? So which is why I have said I will assume a 1 Hertz sampling rate throughout, because it allows, I can now not carry fs and 2 pi fs and all this other stuff, which will surely land me in some numerical mistakes. Okay, so it makes sense to do everything with 1 Hertz sampling rate. Alright, and then you know that you are not going to be building 1 Hertz sampling rate type systems, right? So if you want to build something at 4 megahertz, it doesn't mean that you go back and then recalculate everything. All that you need to do is replace s with s by 4 megahertz. Okay? Yes.
So there is
yes.
What is h of t by 4? Should it be h of 40?
Oh, I'm sorry. This must be h of 40. Yes, it's compressed in time. Correct. All right. Okay. 4h. To make the integral the same, there is a constant. I think the height has gone up. It has to. The time width has gone down. The area under the pulse must be the same, so it must go to. But the key point is to see that the pulse shape has shrunk. You understand? So it's like this. Okay. Today, to get a piece of paper from my office to ad block, from ad block to my office takes anywhere from 15 to 20 days. Okay. You may not believe it, but it is true. I've gotten couriers from the US faster than I've got paper from ad block to my office. Okay. So the question is, how do you fix it? Right? One, you have quicker people. If all the people in the chain were, twice as fast, what do you think will happen? Instead of taking, whatever, 20 days, it will take 10 days. You understand? But nothing will happen beyond that, right? So the only solution is to actually fix the system and, make sure that it doesn't hop from over, 150 desks with, signatures of everybody in the pipeline. You understand? So if you make every component in a network twice as fast, and if you keep everything topologically the same, then what would take a time t, what would happen at time t earlier would happen now at time t by 2, right? So, that's all that this is saying. You understand? So, this is very familiar with very similar to what you do in electrical networks. In your Van Valkenburg textbook, you find that all the networks are 1 Henry, 1 Farad, 1 ohm, and you do all these nice Laplace transform type calculations. So why are they not? Everybody knows that 1 Hertz and 1 Henry and 1 Farad are not practical numbers, right? But still, why do they do them in the textbooks? Because they know that even with 1 Hertz and 1 Farad, you guys make mistakes. So if given 50 Hertz and times 2 pi and all that, forget about it. There'll be only completely crazy results. Okay, so carrying all these numbers doesn't make sense. Okay, but you know that real frequencies are much higher. That doesn't remove any glory away from the theory, right? All that you need to do if you want to make this network have the same behavior but at some other frequency is to simply scale all the element values by the appropriate number. Okay, that's called frequency scaling, that you know already. Okay, so that is, this is exactly frequency or scaling, which is the same as time scaling, correct? In a sample data network, it's where there is sampling going on in the, alright. So if everything with dimensions of time, so all time constants scale by the same factor, right? If which means that even the sampling time scales by the same factor. If everything with dimensions of time scales by the same factor, then the response will get, especially if you sample it at again the sampling rate, you will find that everything remains the same. Okay, so so which is why we will do all these calculations with only sampling rate of 1 Hertz. Another practical problem which I have highlighted in many of my classes before and people still continue to make mistakes is that when you are implementing things in MATLAB, it does not make sense to work with if I gave you an assignment saying you do something with sampling at 1 gigahertz, okay, it does not make sense to take 1E9 as the sampling rate, because if you take 1E9 and let's say you had a 4th order filter, then you will have something of the form s by omega naught whole to the power n. Okay, so does this make sense? If I wanted you to find the coefficients of a filter, of a 4th order filter with a s by omega p of 1 gigaradian per second, if a 4th order filter would have something like this, right? S by omega p blah blah blah. Okay, rather than work with 2 pi into 10 power 9. Okay, what is the problem with working with 2 pi into 10 power 9? Yeah, 1 over 10 power 9 times whole to the power 4 will be of the order 10 power minus 35, which is the smallest number you can represent it in MATLAB. Okay, so the moment you write a polynomial, if you try to find its poles by finding the roots, you will find that you will get some crazy results because of this number is too small. It will treat it as 0. You understand? So this is another practical reason why you should never work with frequencies, which are very large or very small. You always scale your characteristic frequency to be 1, so that all these numbers will have reasonable values, so you don't get into issues like truncation or round off errors in numerical programs. Once you've finished all the calculations with 1 Hertz, then it's very straightforward to scale the whole thing to any frequency you want by simply, if you get inductors and capacitors, which are where everything was scaled to 1 Hertz. If you want to change everything to gigahertz, then the straightforward way is to convert every inductor to, if you got it in henries, you will get nanohenries. If you had farads, it will become nanofarads. You understand? Okay. So in all your delta sigma work, it also makes sense to not to work with absolute frequency. You always normalize everything to the sampling rate, so that the sampling rate becomes 1 hertz. You do all the math, find the NTF coefficients, find the loop filter transfer function and all this stuff, and then you go back to the real world. You understand? I think it's better not start the next topic. I will stop.